In the previous video, we took a close look at the different substitution pathways of electrophilic aromatic substitution. Specifically, we investigated the arenium ions in these different substitution pathways: the ortho-arenium ion, the meta-arenium ion, and the para-arenium ion. We tried to understand how the R groups in each of those will affect the energy of those ions. And that was really in an effort to better understand how electron withdrawing groups and electron donating groups may direct substitution to certain positions around that ring. And we came to the conclusion that electron donating groups are activating, which means they speed up the reaction, but they also direct substitution to the ortho and para positions. Electron withdrawing groups, on the other hand, are deactivating, which means they slow down the reaction, and they direct substitution to the meta position whenever substitution does occur. What I'd like to do in this video is apply that knowledge to develop an energy diagram that compares each of those pathways, right? The ortho-para substitution of electron withdrawing groups versus the meta substitution of electron withdrawing groups, right? Versus the ortho-para substitution with electron donating groups. So what I have here is the energy diagram for the electrophilic aromatic substitution of benzene, right? And we've all seen this energy diagram before, right? We know it's a two-step process, right? We generate the arenium ion in the first step, and in the second step, the elimination, we re-aromatize to give us our product, right? And so this is the reaction here. I'm not showing any specific position because on benzene, all of those positions are the same, okay? Remember, the first step is the rate limiting step. So this is the only step, the generation of the arenium ion, the addition of the electrophile and the arene. That is the step that determines the rate of the reaction. The lower this activation energy, the faster the reaction. The higher the activation energy, the slower the reaction. So how do electron withdrawing groups compare, or benzene rings with electron withdrawing groups compare to the electrophilic aromatic substitution of benzene? Well, we know that whenever we have an electron withdrawing group on that benzene ring, donating group, whenever we have an electron donating group on that ring, these reactions are going to happen more quickly because with an electron donating group on the ring, overall the arenium ion is going to be more stable. We can put more electron density into the arenium ion. All right. We also know that electron donating groups are ortho-para directors, meaning that the products that we'll make whenever these undergo electrophilic aromatic substitution will be products where substitution occurs in the ortho and para position. So here's the ortho product. And the para product, right? Relative to benzene, this is going to be a faster reaction, right? And the reason why it's a faster reaction, again, is because the arenium intermediate is stabilized by the electron donating group. Okay, so maybe we'll draw that intermediate down here. And when we connect the starting materials to the product, remember that we have to go up over some transition state and down the other side. All right, so this lower transition state indicates that this is going to be a faster reaction, right? More reactions are going to happen over the same period of time as the benzene reactions, right? And then down the other side. Okay, so this is electron donating groups, ortho-para substitution. Right? Electron donating or electron-rich arenes can also undergo meta substitution. So we'll draw out the scheme. Substitution occurs in the meta position. Right? And I want you to think about where we would draw that pathway, or where we would put that intermediate on this energy diagram, that rhenium intermediate that is generated from meta substitution of an electron-rich arene. So pause the video, think about it, and then when you have an idea, start the video again. So where that electron-rich arene would go, or where that reaction would go, meta-substituted arene would be in between benzene and the ortho-para substitution, right? So ortho-para substitution is going to be faster than the electrophilic aromatic substitution of benzene, right? Meta-substitution is also going to be faster than the electrophilic aromatic substitution of benzene. The reason why we get ortho-para substitution on electron-rich arenes is because of these two reactions, of these two pathways, ortho-para versus meta, the ortho-para pathway is lower in energy. Right? So with the lowest activation energy, that's going to be the fastest reaction pathway. So here's the electron donating or the electron-rich arene when it undergoes meta-substitution. Here's the electron-rich arene when it undergoes ortho-para substitution. Right? Both are going to be faster than the electrophilic aromatic substitution of benzene. Right? But the ortho-para substitution will happen much more quickly than the meta-substitution. Right? What about the meta-substitution of an electron-poor arene? So now, rather than an electron-donating group, an electron-withdrawing group. Well, if we hit this with an electrophile, we know that electron-poor arenes prefer to undergo meta-substitution. Just caught this mistake here. Tend to go undergo meta-substitution, right? And so because we're generating something that's positively charged, and there's an electron withdrawing group on that thing that is generating positive charge, we would expect those rhenium intermediates to be higher energy than benzene, right? And higher in energy than the electron-rich arenes. So as a result, the activation energy, the transition state that leads to that arene, is going to be higher, and therefore the rate of that reaction will be much slower. Right? So this is an electron withdrawing group in the meta position. Right? And then finally, I want to look at the ortho-para substitution in an electron-poor arene. Alright, so here's our ortho product, and then the para product. Alright, so where do you think that would go on this energy diagram? Well, this is a very high energy intermediate, right? Because we're generating an rhenium ion with an ipso cation. And in many of the electron withdrawing groups, we'll have two cationic centers right next to each other, right? At the very least, we'll have two positively charged atoms, either formal or partial positively charged atoms right next to each other. So therefore, this is going to be the absolute highest energy pathway of those four, right? As a result, right, highest energy intermediate is going to correspond to the highest energy transition state, and therefore the slowest reaction. All right, so here's a ranking, therefore, of our reactions, right? So if we think about the order in which these were written, the reactions up top are going to have the fastest rates. The reactions at the bottom are going to have the slowest rates. In the next video, we're going to take a look at some specific reactions to see how these reaction rates are manifested in the product distribution, in the actual regioselectivity of nitration.